Okay. Cool. I'm going to operate under the assumption that everybody is able to open that lab. Oh man, I cut my head off. Oh well, I'll scrunch down a little bit. Please keep in mind, we're doing this lab together, but you have got to record your own individual results on that Google document. Okay, so if you are right now not with us and just pretending you can open the document, you're going to create a lot of work for yourself outside of class to get caught up. This is a lab, right? This is going to go in the gradebook as a lab. We haven't done a ton of these, which means these are really important points. It's going to carry a fair amount of weight. All right? On your Google Doc for the lab today, you have a prediction question. And I want you to do that right now. Towards the top, part 1, it says, suppose you mix equal masses of water. One sample is 0 degrees Celsius. The other is 50 degrees Celsius. What do you think the final temperature of that mixture will be? Please take time now and make your prediction. One sample of water is close to 0 degrees Celsius. The other is 50 degrees Celsius. What are they going to end up being? Take a minute and type your answer in. Can you hear this water boiling, or is that just me?
Just you right now.
Okay, that's good. I didn't want it to be background noise that made it difficult to hear me. So we're going to test out your prediction as close as we possibly can. For part 2 of the lab, we're going to do this. We're going to take some cold water, we're going to take some hot water, and we're going to mix them together, right? But in order for this to be accurate with our prediction, even if I can't hit those exact temperatures, I have to get the same mass of water. So I've got a graduated cylinder. This is the best tool for me here in a science classroom to measure the volume of liquids. So I have an ice bath right here. This is really cold water that has been sitting in an ice bath now for most of the class period, okay? Even before we started. And so I'm going to pour this into the graduated cylinder, over the sink, of course, because that's responsible. And I'm going to get 100 milliliters. Boom. 100 milliliters of very cold water, and I'm going to put that in my cup labeled cold. Imagine that, right? Perfect. 100 milliliters. Now I'm going to take this temperature sensor. I'm going to put the temperature sensor in that cold water so we can get a reading. And I am going to have you record in that table the temperature of the cold water. Okay? While that temperature sensor is adjusting, I have this water that's been boiling for a long time. I'm going to very carefully measure out 100 milliliters of that. We want the same mass of hot water as we have cold water. That's really important. The temperatures are going to be drastically different, but we don't want the mass to be different. There we go, 100 mils of that. So ladies and gentlemen, on your lab write-up, part 2, where it says cold water temperature in Celsius, would you please record 4.5? That's the temperature of the cold water, 4.5. Okay, now we need to know the exact temperature of the hot water. And so I'm going to pour that into the styrofoam cup. We use styrofoam cups because they're good insulators. Heat does not transfer in or out of these styrofoam cups particularly well. Yes, they are open to the air, and so that heat energy does eventually dissipate. but it's a little bit slower than if I had some other type of cup. In the table now, this is where we're going to record the temperature of the hot water before we mix the two together. And we are getting 77.5. Please record that in your table. 77.5. That's the temperature of our hot water. Before your very eyes, I will now take the hot water and mix it directly into the cold water. I will use the temperature sensor as my stir stick, and we're going to see where the temperature ends up. This will be the third box in your table, the mixture temperature. All right? What is the temperature of the hot water and the cold water once they mix together? We'll give that just a few more seconds. Let's go ahead and level out. Okay, folks, we are at about 39.5. 39.5 is the temperature of the mixture. That'll be your third box. Just taking a look at the chat. Look at this, people helping each other out. I like that. I appreciate that. Thank you very much. The mixture is the hot water and the cold water together, and it was 39.5. 39.5. Okay. I know that this was not particularly entertaining. There was nothing on fire or exploding or anything that was wildly amazing. But there was a relatively simple concept here. Does anybody notice anything interesting about the mixture temperature when you compare it to the hot water and the cold water temperatures at the beginning?
When we mixed them, they came to like a middle temperature in the middle, but it's still colder than the original hot.
Correct. Colder than the original hot, but isn't it also hotter than the original cold?
Yes.
Yeah, those two temperatures should have met somewhere in the middle. Okay, very, very close, because we took 100 milliliters of cold and 100 milliliters of hot. They should have ended up somewhere in between. So for part 3, we've got a couple of thought questions. Please take a look at those. Thought question number 1 says, did the results of this experiment agree with your prediction? Well, we didn't have 0 degrees Celsius and 50 degrees Celsius. You're going to have to kind of just go with me here for a second. Did your prediction show that the temperature would, did you say that it would end up at 25? Did you think that in your prediction it would end up somewhere in the middle? Okay, very close to the middle point. Or did you think the temperature would be closer to the cold or closer to the hot? Okay, so please answer part 3A. Did the results of your experiment agree with your prediction? Although the numbers might be different, I want you to answer that question as if, did our actual data here represent the same pattern? In other words, our numbers ended up right smack dab in the middle of the original cold and the original hot. Is that what you predicted would happen, even if the numbers would be a little bit different? Okay? If it didn't, then say, no, it didn't. My prediction was different. It was off. Okay, we've got anyone else having trouble seeing or hearing? Any technology issues today? Okay, feel free to log off and log back on. Go ahead and open this up. If anyone needs to reboot, go ahead. I am recording this now so that I can provide this later for students that aren't here. Okay, let's take a look at B, part 3, B. Part 3B says, how do you think your results would have been different if you had used more hot water than cold water instead of equal masses? Okay, give me your thoughts there. Relatively simple setup, but we used 100 mils of cold and 100 mils of hot. How would our results have been different if I had used way more hot water than cold water? Any suggestions, any thoughts?
Well, if we used more hot water than the cold water, then wouldn't the end result be warmer water than the cold water in the first place, but it'd still be colder than it started?
So you think that the temperature still would have ended up somewhere in between, but it would have been closer to the hot water temperature? Is that correct?
Yes.
I like that. Any other thoughts there? How do I pin mine? Come on now. No other thoughts? Okay. Take some time to type your answer in for B there. What do you think would happen if we used way more hot water than cold water? Okay. Still water, still really cold and still really hot, but what if the amounts we mixed were not equal to each other? What if we used a gallon of hot water and just a small cup of cold? Tell me where you think the temperature would end up approximately. All right, now's the time for questions, concerns, repeated data, anything at all. Please be an active learner right now. If something isn't making sense or you're lost, please ask, because I guarantee you're not the only one. All right, I appreciate people helping other people out in the chat with the data. When it comes to your thought questions, folks, make sure that you're not taking somebody else's info. Make sure you're not letting them do the heavy lifting, because then you won't be any different after this lab is over. Okay? We're going to move on to part 4. Part 4 is similar but different. It's asking for another prediction. Here's what we're going to do. Part 4 says, what if you mix equal masses of cold water and hot metal this time? Not water. We're going to take cold water and hot metal. Will the final temperature follow the same pattern as the experiment did in part 2? Okay? So let me explain this real quick. We're going to take a metal cube and heat it up. And I'm going to take a mass of water that's equal to the mass of the metal. Okay? So we'll have mass the same. One very cold, one very hot, and then we're going to mix them together. What I'd like you to comment on is, do you think the temperature will end up smack dab in the middle again? Will it be closer to the cold water? Closer to the hot metal? Do you think something weird will happen where the temperature will end up colder than it ever was? Will it end up hotter than it was for any of the substances? Tell me what your prediction is. Please take a minute or so right now and record that on your actual Google document. Okay, we ready to begin? Please speak up, folks, if you can't see, can't hear, or are just not ready. All right. Hot cup is empty. I'm going to take the cold cup, which had our mixture. I'm going to go ahead and dump that out. So now we have 2 empty cups. Now we got to treat this one a little differently because it's not water and water. Now we've got water and metal. I have right here an aluminum cube. This aluminum cube, we used this for the density lab earlier in the semester. It looks like this. Okay. This aluminum cube is the one that we're going to heat up. Now we're going to use this idea of thermal equilibrium. What that means is if I put this metal cube in hot water and I leave it long enough, eventually the cube and the water will reach the same temperature. So we're going to go ahead and do that now. I'm going to go ahead and take this cube and I'm going to place it in my hot cup, which is empty right now. I feel like I'm doing a magic trick. Watch where the cube goes, right? And then I'm going to take this really hot water and I'm going to put plenty of water in this cup so that it covers the cube and more. All right? Now, right now, before your very eyes in this cup, what is happening is that thermal energy is going from the really hot water into that cube. The cube is heating up, the water is slowly cooling off, and they're going to end up at exactly the same temperature if I give them enough time. We're going to go ahead and give it like a minute or two so that that thermal equilibrium is reached there. Okay? Now the metal mass. Please take a look at your table for part 5. I put that aluminum cube on a digital scale. I don't know if you can see this on the board? Probably not. It's pretty tiny. 45.61 grams. That's the mass of the metal. I just used the digital scale for that, okay? Nothing fancy. Please record that on your table for the mass of the metal in grams. 45.61. Okay, someone feel free to post that in the chat so everybody can easily read it. Now, our temperature sensor. I'm going to place that in the water here. And if I let it sit in there long enough, this will tell us what the temperature of the metal and the water eventually become. Remember, they're going to reach thermal equilibrium. While that's happening, I've got to measure out cold water, but I need the same mass of water as I have mass of metal, right? And so if the metal mass was 45.61, I got to get that much cold water as close as I possibly can to 45.61, okay? So we are in part 5 right now. We're moving along pretty quick here. On your Google document, we're in part 5, and there's a table. It's right after the prediction you should have made. If you're following along with us, folks, we're just doing one section right after the other. So right now, in the table on the bottom, you should have the mass of the metal, and that should be 45.61. And that's all we have in there right now. Okay? I'm going to take the cold water. Remember my ice bath? I got my ice bath right here. I need to measure out as close as I possibly can about 45.5 grams of water. Now, luckily, I don't know if you realize this, I'm not going to stick that on a scale. 1 gram of water is equal to 1 milliliter of water. So if I can get 45.5 milliliters of water in here, that will equal about 45.5 grams of water. So I don't have to put anything on a scale. I can go ahead and just measure this out. Let's see if I can get close to 45.5. And I'm a trained professional. Please do not try this at home. If you do, you might get DHMO all over you. Boom. I say boom, but I didn't get it exactly. It was just close. Let's check that. Awesome. I'm at about 45.5 grams of water. Okay? Now, stay with me here. On our table on the bottom, right in the middle, we have cold water mass. Okay, right in the middle, cold water mass. I just measured very carefully to try and make that exactly the same as the metal mass. So I'm at about, I can only tell you, I'm about 45.5. So your mass of cold water, 45.5 grams. That should go right here on your table. Okay, mass of cold water, 45.5. I know it's not exactly 45.61. I don't have the tools with me here to measure that exactly, but we're going to be pretty darn close. Okay, mass of cold water is about 45.5 grams. So now let's get the temperature of the metal mixture and the temperature of the cold water, and then we're going to put those together. So I've got the temperature sensor in my hot water right now. Remember, the hot water and the metal cube have been in contact now for a couple of minutes. So we're going to make the assumption that the metal cube heated up and the temperature of the hot water dropped a little, and they are now equal to each other. So on our table, this is going to be the metal temperature before mixing, and it is 72 degrees Celsius. That's metal temperature before mixing, 72. Okay, now before that cools off too much, I got to get the temperature of our cold water. So I'm going to go ahead and do that now. On your table, this will be the cold water temperature before mixing. Cold water temperature before mixing. And I'm waiting. Ten point five. 10.5, ladies and gentlemen, is the cold water temperature before mixing. Now, I got to get this metal in there quick. I don't want the temperatures to change much from what I measured. So I'm taking my hot metal, getting as much water off as I can, and I'm putting the hot water into my cup with the cold water. Right now, I imagine that there is heat being transferred from the metal cube to the cold water. What I'm trying to figure out now, though, is when the water and the metal now come to equilibrium, where is that temperature going to be? Okay? Well, this is happening. It'll just take a few more seconds. Look at what the temperature of the cold water was. What did we say? 10.5?
Yes.
Okay. And what was the temperature of the hot metal?
72 point. Yeah, just 72.
Okay. So if your prediction was that the temperature now of this hot metal and cold water mixture would end up smack dab in the middle, that would put us somewhere around, what, in the 30 to 35 range-ish? Right? Is that right? 70, 60, 30, no, somewhere around 40 degrees Celsius, right? And we're going to see if that happens. We took the same mass of cold water and the same mass of hot metal, and I mixed them together. Now I'm waiting to see if the temperature normalizes somewhere. And it does. Ladies and gentlemen, this is the very last box on that table, the mixture temperature. And you might be surprised we are at 18 degrees Celsius. 18 degrees Celsius. I don't know how many of you predicted that would happen. We took the same mass of cold water and the same mass of hot metal and stuck them together. And we got a temperature that maybe you were not expecting. Okay? The water did heat up. Maybe just not as much as you thought it should have. Did we end up smack dab in the middle of those two starting temperatures? No way. Not even close. So something weird is happening here. Let's go ahead and take a look at our thought questions. This is part 6. Part 6, question A. Well, let me pause real quick. Does anybody need a reminder of any of the data? Did anybody not get the data written down? The mixed temperature, or the mixture at the very end, was 18 degrees Celsius, 1-8. Okay, now folks, you might have gotten tired of me saying this last week, but I'm going to say it all this week as well. It's going to help me sleep at night, okay? What we're doing right now is preparing you for the final, not a part of your final, the whole stinking final exam, right? It's just going to be a unit test. So more than any other test in this class, it is important right now that you are asking questions if you're stuck, okay? Not pretending that you get it if you don't actually. Because we don't have weeks to work with here. We have 1 week. We have this week. That's it. By the time Friday hits, our time to teach you new material is gone. That time to prepare, out the window. You'll show up next week and you'll take your final for this class. So I need you to be asking either through the chat or by unmuting if something doesn't make sense. Let's take a look at question A. We're in part 6. Question A. Why didn't the temperature of the water and aluminum mixture come out halfway between the temperature of the cold water and the hot aluminum cube, even though we mixed equal masses? Man, I'm coming right at you with this question, right? I'm coming right at you with this question. Hot metal, cold water, we stuck them together, but the temperature did not end up smack dab in the middle. The temperature ended up really close to the original temperature of the water, okay? The water heated up, but just a little bit. And for A, I'm asking why. We can think through this. Does anybody have anything to add to this or a specific question to ask that's going to help us answer question A?
Could it be some aluminum versus different metals could have affected this?
If we used a different metal, we would probably get a different result. Okay, that's actually what we're going to show you in class on Wednesday. We're going to run something very similar, but we're going to test other metals. Okay, but right now we don't have that data to go off of. So we just have to compare it to the fact that we took hot water, cold water, and stuck them together and the temperature ended up in the middle. But if I take hot metal and cold water, the temperature just barely changes the water temperature, just a relatively small amount. Does anybody know why?
Is it possible that the aluminum cube could have absorbed the heat?
It did when we were making it hot. Okay, when we put the cube in the hot water to raise the temperature up, the cube was absorbing heat. When we put that hot metal into cold water, the aluminum cube is giving that heat away. Okay, it's definitely getting rid of its thermal energy. Okay, so folks, why would they have not ended up in the middle? Don't make this more complex than it actually is. The relatively simple answer, if you'll just let your brain tell you logically what's going on here, why would the mixed temperature not end up in the middle? Right? One's a solid and one is a liquid. We're getting close. There is definitely something different about these two materials.
Could it be because since it was just like the cube, it was in just one spot compared to like the water that was like all around?
I
Like
like
once it
that
was
idea. Right?
it
The
like
liquid, I'm sorry, I cut you off, Perla. Continue.
no, that's all I needed to say.
The liquid's flowing, it's moving, right? And the solid has its atoms that are locked in place and they're just kind of vibrating next to each other, but not moving significantly. Okay, that's a true statement. Does it explain why the temperature of the water would have changed just a little bit? The temperature of the metal changed a lot. It cooled off a ton. What was the starting temperature of that hot metal?
72 degrees.
70 degrees. Do you know what the temperature of the metal was at the end?
I'm assuming that means it would be our final temperature, which would be 18 degrees Celsius.
It's exactly the same temperature as the water at the very end. So the temperature mixture, when we said it was 18 degrees at the very end, that's the temperature of the water and the metal together. They reached thermal equilibrium. Why did the temperature of the metal drop so much and the temperature of the water only raise a little bit? Okay, that's what the question is asking here. Why would the temperature of the water and the mixture not end up in the middle? Come on, somebody dig this one out.
Does this have something to do with the space between the atoms of the solid object versus the liquid?
So not necessarily, but not the space, but the atoms themselves, yes. Absolutely. Ladies and gentlemen, what was actually transferred from the cube into the water?
Thermal energy?
Thermal energy. Remember, are thermal energy and temperature the same thing?
No.
They are not. So just walk through this with me. If the water temperature only changed a little bit, how much energy, how much thermal energy did the metal cube give to the water?
A small amount.
A small amount. Holy cow, okay, we're getting there. If I mix water and water, same mass, same substance, but one's really hot and one's really cold, they meet right in the middle. If the metal gets put in the cold water and the water only heats up a little bit, it's a simple explanation. The metal only gave the water a little bit of thermal energy. That's it. Our answer for A, take a look at that question again. Why didn't the temperature of the water and aluminum end up halfway in the middle? The metal cube only had a small amount of thermal energy. That's it. And if you're looking at me and saying, but its temperature was 70 something Celsius, remember, temperature is not the same as thermal energy. They're related, but it's not the same. It's not transferring Celsius degrees, right, to the water. It's transferring thermal energy. The cube must not have had very much thermal energy. All right? If you're having trouble putting it into words, let's see if we can nail this down for A. Okay? The metal cube transferred thermal energy to the water. Just not very much. That's it. That's it. Any questions on A? Okay, everybody that said stuff about, well, solid versus liquid, the atoms and the spacing, you're getting at something that is probably the most complex idea of the whole unit. We're going to reveal that on Wednesday. Something called specific heat. Not every substance can hold the same amount of thermal energy. Okay, so we'll get to that. Let's take a look at B. Explain what is happening between the aluminum cube and the water in terms of temperature and thermal energy. We already alluded to this. Which direction is the thermal energy going? From cube to water or from water to cube?
Cube to water.
Cube to water. Okay? So for B, you would need to say thermal energy goes from the cube to the water. That's the first part of your answer. There's two parts to this. Okay? Thermal energy from the cube to the water. Okay, now here's the second part of that question, because we commented on thermal energy, but we didn't comment on temperature. So yeah, I'll repeat that real quick. For B, thermal energy goes from the cube to the water. Okay, but what about temperature? What happens to the temperature of the cube? Come on, whole class. What happens to the temperature of the cube when we put it in the water?
The temp dropped.
Drastically, right? In order for it to level out with the water temperature, that 70 degrees Celsius cube ends up at 18. So the temperature of the cube drops. And what happened to the temperature of the water, even though it was only a little bit? It increased. Okay, so make that the second part of your answer for B. The first part is thermal energy goes from the cube to the water. The second part of your answer is the cube temperature drops and the water temperature rises. Not the same amount, but that's what happens. Cube temperature drops and the water temperature rises. Only 2 questions left. Great time to ask questions if something isn't making sense. Okay. C is the easiest question of them all, but it looks like the hardest. Let me read this through, okay? This asks, how much energy does it take to raise the temperature of 1 gram of aluminum by 1 degree Celsius compared to raising the temperature of 1 gram of water by 1 degree Celsius? What in the heck is that question asking for? It's the definition of a word we haven't taught you yet. It's called specific heat. Okay? I need 2 volunteers. Give me a thumbs up if you're willing to be one of our volunteers. I got 1 volunteer. I just need 1 more. Oh, perfect. Now I can't see behind my recorder. Who is that? Who is our second thumbs up? I got Jed, and who else? I got a window popped up and it won't let me move it. I can't see who keeps giving me a thumbs up. Let me know in the chat who you are. There we go. Awesome. Michael V, I appreciate it. Here's what I'd like you to do. Jed, would you get on the World Wide Web of information? And I'd like you to Google, I'm putting a term in the chat right now. It's called specific heat. Would you please look up, just do a Google search for specific heat of aluminum. Okay? And Michael, if you would go ahead and do the same thing, but do specific heat of water. And I want the two of you to come back and put the numbers in the chat. It might look like a crazy number with all sorts of weird units. Type it as best you can in the chat once you find it. This is going to be the focus of our class on Wednesday, this idea of specific heat. It's a little bit mind-bending, but we're setting the stage for it right now. Okay? There's no calculations for C. All it's asking for is, what is the specific heat of aluminum? And what's the specific heat of water? And that's what Jed and Michael V are getting for us right now. You guys feel free to type that in the chat as soon as you have it. There we go. So Jed's got a number there, 0.91. Now, Jed, the best you can, are there units tied to that number? Are there joules and Celsius or Kelvin divided by gram? Tell me what the units look like that go with that number.
kJ divided by kilograms K.
Good. Awesome. Okay, so we have to adjust these just a little bit. Michael, there's nothing wrong with your number, but we're in two different units of measurement. So I'm going to change these real quick, okay? Jed's number is 0.91. And folks, you can record that on your lab. That's the specific heat of aluminum. And Michael, I'm going to adjust your number just a little bit. We're going to go 4.182. That's our specific heat of water. All right, now here are the units, folks. I'm going to type these in there. This is joules per degree Celsius times grams. And let me tell you what witchcraft and wizardry we just used for this. Here's what you actually recorded. The one for aluminum is 0.91. 0.91. Same units, just a different number for aluminum. Okay, and here's what these numbers mean. Listen carefully, because this will be our main idea for Wednesday. If I want to heat up aluminum, and I want it to go up just 1 degree Celsius, I have to put in 0.91 joules of energy for every gram of aluminum to get it to heat up, right? Okay, that might not mean much to you right now, but just know if I want to heat up aluminum, I can heat up aluminum. I can stick it in the oven, and I can heat it up. If I want to heat up water, though, I can add heat to it, but I have to add 4.182 joules for every gram of water to get it to increase its temperature. So here's what I'm getting at. Here's what I want you to realize. If you want to heat up aluminum, you put thermal energy into it, and its temperature will rise. If you want to get water to heat up, you put thermal energy into it, and its temperature will rise. But they do not require the same amount. Aluminum heats up very easily. Water takes way more energy for its temperature to change. In other words, you can put a ton of thermal energy into water, and its temperature will only change a little bit. It has a very high specific heat. Aluminum has a very low specific heat. That's what C is asking. Right now, it's just numbers. It will make more sense to you on Wednesday, but I want you to think of this. What is most of your body made up of?
Like 70% of water.
It's a ton of water. And this is very, very good, and here's why. Water has a very high specific heat. It does not change its temperature very easily. It doesn't heat up easily, and it doesn't cool down easily. You've seen this, folks. When you make soup, when you make ramen noodles, when you put your water on the stove for your mac and cheese, you can crank that heat up all the way to high, and you can put a big pot of water on there. How long does it take to boil?
10, 15 minutes.
You have got to pour energy, tons of energy into that water, and its temperature slowly changes. If you put a piece of aluminum foil on that same flame, do you know how long it would take for that metal to heat up?
A few seconds.
It's going to heat up really quick. Aluminum foil heats up real fast. When you take it out of the oven or away from the flame, it cools down real quick. Okay? Water takes a long time to heat up, tons of energy, and it takes a while for the energy to leave it as well. This is very good for your body because if you walk outside on a hot day, because you are made up mostly of water, your internal body temperature will not change very much. If you go outside on a cold day, even if you're shivering, your internal body temperature will not cool off very much because you're made up mostly of water, and water does not change its temperature very quickly. It stores a ton of energy, and that is very, very good. Otherwise, you'd walk outside on a cold day, you get hypothermia right away. Or you go outside on a cold day, you get heat exhaustion immediately. You don't. And that's because you're made up mostly of water. Last question, D. It says, heat and temperature are related, but they are not the same thing. According to your results, what does the concept of heat energy take into account that temperature does not? Right? So in other words, we can measure the temperature of aluminum and we can measure the temperature of water. We can even get those two exactly the same. But when we're talking about heat and heat energy, what does heat energy seem to take into account that temperature does not? Any thoughts there?
The specific temperature of heat, specific heat, it doesn't take into account of that.
Close. Close. It's related to specific heat. If I measure the temperature of the metal and I say it's 50 degrees Celsius, and I measure the temperature of some water and it's 50 degrees Celsius, do those two things have the same temperature?
No.
They do. I just said they were both 50 degrees Celsius, right? You thought it was a trick. The trick's coming, right? If I have a piece of metal and it's 50 degrees Celsius, and I have a sample of water and it's 50 degrees Celsius, do they have the same temperature? They do. They're both 50. Do they have the same amount of thermal energy?
That's a no.
No. So what does heat seem to take into account that temperature does not?
Thermal energy?
Close. It's what the material is made out of.
Oh.
That's it. When we talk about thermal energy, it totally depends on what the material is made out of. Temperature doesn't make any difference. You can measure the temperature of your nose. You can measure the temperature of water. You can measure the temperature of the air. Temperature doesn't take into account what it's made out of, but heat does. So for D, what does the concept of heat energy take into account that temperature does not? What the material is made out of. That's our answer for D. Okay, you could say what the substance is, the types of atoms that make it up, all of those would be perfectly acceptable. Okay? Now I'm guessing. Oh, for C, gotcha. The question was, what are we typing for C? We're typing the number for aluminum. You should type 0.91. Okay, so you want to tie that number to aluminum. So I'd probably type aluminum 0.91 and then water 4.182. Okay, those numbers can be found in the chat just a little further up. I wanted you to see that the specific heat for aluminum is a small number. And the specific heat for water is a larger number. You might say 4.182, that's not a very big number. It's pretty big when you compare it to 0.91. Okay, it's more than 4 times as much. For water, it was 4.182. That's our specific heat for water. Does anybody at home, have you seen your water heater before?
Yes.
If you are in a position to go find your water heater, if you live in an apartment complex and there is a water heater that provides water to multiple units, right? Maybe, I don't know, maybe you know your landlord, maybe you can ask them. You ought to go take a look at your water heater. Mine just broke this summer. Stupid water heaters. They're expensive to replace. But ladies and gentlemen, when you turn on the hot water, you got to wait a little bit for the warm water from the water heater to make it to wherever you are, okay? If your bathroom sink is really close to your water heater, you could turn the hot water on and you get hot water in a matter of seconds. If you are floors away, right, or very far away from your water heater, you turn that hot water on and you got to wait, and you got to wait, and you got to wait, right? A water heater heats up a ton of water. Unless you have a tankless water heater, that's a discussion for another day. Those are more expensive because they're pretty darn slick. But ladies and gentlemen, it is very difficult to heat up water. And if you're trying to heat up a ton of water, it takes a lot of energy. So what people have to pay a heating bill for, not just to heat the air, but to heat the water in their water heater. So that you have the luxury of turning on hot water, waiting a few seconds, and then magically warm water just kind of shows up for your shower or in your sink, right? But it takes a ton of energy to heat that up. Think about how long it takes for a pot of water to heat up on the stove. Now imagine 40 gallons of water to heat it up and to keep it warm all the time. If you live in a household with more than one person, you might have had someone use all the hot water before. That doesn't mean there's not any hot water in the world. It just means that they've used up all the water that was in your hot water tank, okay, your hot water heater. And now that fills with water and it takes time for it to heat back up. You gotta wait 30, 45 minutes, sometimes an hour before you get hot water again. All right. If you followed along, you're probably ready to turn this in for points. If you have questions, now is a great time to ask. All right. The last item for you to do is in the daily deal. Let me screen share real quick and we'll show you what that is. Let me get to the daily deal. You can go there as well. I have some practice problems and you got the remainder of the time today to work on them. Folks, I can't stress this enough. If you are thinking, I just want to get out of this class, I have no intention of doing those problems, then in less than a week, that goes in as a 0, right? And at the end of the semester, there's not a darn thing you can do about it. I don't mind if you do this on your own or if you do it while you're connected to WebEx. I need to verify attendance real quick, so don't leave just yet. But folks, I want you to try these practice problems, okay? They are the thermal equilibrium practice problems. They're in Canvas. It's going to look like a quiz. It's not a quiz. It's just an assignment. I have it set for you to try up to 10 times if you want. Canvas will keep the highest score, so there's no risk to try it more than one time. Let me verify attendance, folks, and then you can log off and work on these on your own, or you can stay connected in case you want to ask questions about them. Okay? Let me verify attendance, and then you can choose to do either one of those options. Okay, I've set this assignment to be due on Friday of this week. Please don't wait that long. I would probably encourage you to practice these before you come to class on Wednesday. The remainder of the time is yours. I will stay connected here the whole time so you can ask about the lab or the quiz questions, which are not really quiz questions, just practice problems. If you'd like to disconnect, you can. Please make a choice that's best for you. Okay, Jed, I will finally answer your meteorology-related question. Okay? Here's the hint. A fog bow is essentially a rainbow that does not have the dispersion of colors. Okay? So you see a literal bow, which means the light has to come back to your eyes. The light source is behind you. There has to be moisture in front of you. And you see this bow, but you don't see the colors. So a rainbow has 3 of our vocab words, right? You're going to use all of them except for dispersion. Just use the other 2. Okay? Where did you find diffraction? What was your source? The internet?
Wikipedia.
Wikipedia. Let's go ahead and ignore that for today.
Okay.
And explain it as essentially a rainbow that does not have the colors disperse.
Okay, cool. Thank you.
You bet.